Hi and welcome to class 5. This week we're going to look at one of my favorite subjects, which is particles and espresso. We're going to create our own emitter, emit particles, modify them in espresso, and then feed them on into a dynamic system. Right, so let's get started right away. First of all, we are going to have a look at how to create our own emitter using the Python system in Cinema. For this I'm going to use a Python generator, but you could use anything else. It's just that I find it quite convenient that it's going to run my script every time on frame 0, because I don't want to have too many particles right now to show you all this stuff. Generally you could just as well use a Python tag, which would be more like a normal emitter, because of course the script would be run on every frame, and on every frame we would then emit particles. But for our example, we are going to use the generator for now. Okay, let's look in the editor. It's our default system. This cube, we don't really need this. All I'm using this generator for is just as a kind of like a starter script. So my script is being run on frame 0. So let's get rid of this comment. We don't need that. And let's just return a null object. There we go. So now it's just a blank object that's being returned. Right, so first of all, what are particles? Particles are basically non-geometric objects that contain a number of parameters that are being used in a simulation. Particles in Cinema 4D can have attributes like velocity, size, mass, position of course, and some others. All these parameters or this collection of parameters, which are the particles, they're being stored in a master system. So to get to these particles and to create our own, the first step we have to take is we have to get the master system from Cinema, and feed our particles into it. So how do we do this? Let's look at the documentation. All the thinking particles documentation is in its own module, which is under modules, thinking particles. There we go. And you see here there's only two types. There's the P group and the master system. Actually, I'm going to start with the P group one because it's much quicker to explain. The P group is just what you see when you look in Cinema under the Thinking Particles tab or window that you can see here. It's these groups here. So these groups, they contain particles. So I can create my own groups here, and they work exactly the same as objects in the object manager, so I can move them around. Well, not right now, but if I add another one, right, I can move them around and on different levels and so on. And I can also navigate through that tree here from my Python script. So just like I was able to navigate through the object manager by using the command, for example, get down, to get the next one to get the next object on a lower level, I can do the same thing here. Get down from all would be group 2. For now, I'm going to remove those again. But anyway, those are the groups that you can see here, and you see they don't have many functions or members available. The two that you are going to use most often are num particles and get particles. Num particles just returns the amount of particles that are in each group, and this will return a list of the particle IDs. What we use those for, we will see when we look at the master system. So this will not return the actual particle, it will return the ID of a particle that's in the group. So basically the particles are not actually in that group. The particles are all managed by the master system. The groups are just a list of IDs, and they point to the particle in that master system. Okay, let's go back and look at the master system, and here we see we have a lot more possibilities. Let's begin by getting the master system itself. Each document has its own master system, so it shouldn't be a surprise that the function to get the master system is not part of this TP master system type, but of course part of the document itself, as you can see here. So we've got the base document get particle system function. Of course, we can't, as you may remember from a previous class, we can't call base document itself. We need to call an object of type base document, which is preset in the scene as doc, and use a get particle system to get our particle system. Let's do that. Alright, so we start here. I'm just calling it TP doc get And to see that something's happening, there we go. There you see we got the master system. Alright. Next step is to find out how to add particles. And that's relatively easily done. Again, these functions here, they will help you with that. Let's scroll down and see what they do. Right, so basically all you need to do is call this function, alloc particle. Alloc coming from the C or C++ side, more like the C side. Alloc means it's going to allocate a space in memory for, well, an object, which in our case will be a particle, and it will return the ID of that particle in the master system, just like the IDs that the group would return later on. So we just call that, we get an ID back, and then we can assign values to that particle through these functions here, through these set functions, by using that ID that was just returned. For example, we can assign our particle to a specific group, which within this group list here, or we can just assign it to the all group. We can assign mass, position, size, all these kind of things, and we're going to do that in a moment. One very important method here is setLive combined with setAge. setLive will decide how long your particle is going to be available to you. It's being set through the base time object that you remember from earlier. So we just give it a base time object based on the current frames per second, and that will be how long that particle is available. And when this live reaches its end, then the particle just disappears. Through the use of setAge, you can advance or reverse that stage and make your particle, or set the age of your particle to whatever you want. This is also being used, by the way, to destroy a particle, because if you just set the age to -1, it will be gone immediately. Right, but before we get too far ahead of us, let's just create a number of particles. Okay, so first step now is, well, let's get rid of that print statement. Let's get the base group, which is just the all group. Let's call it TP root. And that's being done by using the master system and getting its root group. And that returns that group here. And then let's just allocate an particle. Let's call it P. And let's see what happens. All right. You may not have seen, whoa, I'm going all over the place here. Okay. There we have it. This very tiny speck here. Actually, let's change this to make it a, whoa. Okay. So that box here now, that's that one particle that we just created. And if we were to do that again, we should end up with 2 of them. Okay. Well, you can't see them because they're all in the same space, and you will notice that we have now a total of 3 and not 2. That's because when you add new particles, the old ones aren't being deleted. They just keep on adding up to each other. So it's only once you go back to frame 0, then at 0 it will clear out the master system, all your particles are being gone, but because we are at 0, that script is being run and our 2 particles are created. So from 3 we went to 2, meaning during this time here we had 3, we went back to 0, then for a second we had no particles at all, then here we had 2 fresh ones created through that script. That's something you really have to keep in mind, because while we are at frame 0, these can keep adding up, and then you can hit that mark here, being the maximum particles, and once you hit that you will get an exception in your console, and none of your particles are going to be created anymore. Then you have to raise that number here. Otherwise you won't get any new particles, it will just stop. And although these are 100,000 particles, that can be hit rather quickly actually. But not with our example today. Anyway, that's something you have to keep in mind when you're emitting your particles and suddenly it stops, then this is probably the reason. Right, let's turn this back to ticks because the box is way too big. And you see here we got that group. We didn't actually use it because we already got our particle in the all group. But if we wanted to assign it to that group, that's easily done by calling TP again, calling the set group. And if this were any other group, we could use it as well, but we will just use the root for now. And we're taking the particle that we just created, and we're assigning it to the TP root. Okay, and once again you see now we have 4 of them. So that particle here will now be assigned to that group. This one here won't because we just overwrote this variable. Now this is a bit boring actually. We just create a number of particles that they just sit there, and this is all no good. First of all, we want to create more than one, so let's create 1,000. So I'm just creating a loop here, and we're creating a particle. This one we don't need anymore. We're assigning the group, and let's assign it a lifetime. And like I said, we have to pass in a base time object. So it's a c4d base time. And let's say first of all 90 frames is a bit too little for a simulation. So let's make 1,000 frames. There we go. And let's have our object last for 1,000 frames as well. So if you remember from, I think it was last week where we had the base time object. So this is going to be 1,000 units if you want, and we have to pass in a divider, which is going to be the get FPS, so that's the frames per second. So this means that this will now last for 1,000 frames. And I think we need another. Yep, okay. So that's the live set. The age of your particle will always start at 0. We could of course set the age to 999. Which would be kind of pointless because then it would only live for 1 frame. But generally you could do that. You could, for example, randomize the age of your particles now so that you get a different lifetime for each. Or you could have, in the beginning, just randomized the lifetime itself. Either way. Okay, so for now, these particles are all being created on the same spot. That's no good as well. So we want to randomize that. And actually to randomize, we should import the random module again, as always. I'm going to set position. And for its position, it expects a vector. So it's a c4d vector. And in here we would pass in the x, y, and z value. And we want to randomize that. You could put all the random functions in here. Personally, I really like to create a small helper function for that because it's much more convenient and much less typing work that way. So let's call it R&D and a multiplier, and then we return random.random, which, if you remember, will return a number between 0 and 1. A floating point number, and we multiply it with a multiplier. So what this does is basically when we call this with R&D 50, it will return a number between 0 and 50. So yeah, it's quite short and really useful. And again, as in previous classes, we should set the random seed to something. Let's take 1, 3, 4, 5. Okay, this is okay because we're only creating whatever we are creating here on a single frame, so this won't change much. If we were to use the Python tag for this, so which means it would be evaluated on every frame, then we would a bit more randomization, because if we leave the seed at this number, then on every frame all particles will be created at the exact same random location. So I think I explained it before, that this random number that's being created here it's not really random, it's pseudo-random. So it's based on that seed number here. So these will always create the very same random numbers. So if we were to use a tag here, we could use, for example, the current document time, and then use that as a multiplier to the seed, or just use the time itself. So on every frame we would get different numbers. Okay, but back to our vector. We now have our random helper function, so we just actually let's use another variable for this. Let's call it radius and make it 50. Okay. So that's our RMB50, and we call that 3 times for x, y, and z. And do we have enough closing parentheses here? Yes, I think we do. Okay, let's see what is going to happen. Let's clean this up. Okay. Compile this, no error. Okay, that's good. Execute. Ah, there we go. So that's much nicer. Now we have a random point cloud here, or a random particle cloud rather. But they're not doing much, they're just sitting there. That's because they don't have a velocity yet, and we don't have anything influencing them. So there's 2 ways to move particles. Actually, there's 3 ways to move particles. One way would be to manually go and loop through every one of these particles again on every frame and set that position to a different position. So you can manually move around the particle and put them at a specific position on each frame. Then, of course, you can simulate them by using expressor thinking particles nodes, or you can give your particles a velocity so they are going to move by themselves, which is what we're going to do now. So after this, you might have guessed it, it's called set velocity, and again it expects a vector, but keep in mind to not make this vector too large, because what velocity does is it's going to add that vector to the position vector on every frame. Meaning if I add 10, 10, and 10 here on every frame, this position will be increased by 10 on x, y, and z, and that can get really fast. Well, in a second, really, it's gonna move out of the screen really quickly. So let's give it another variable here. Call it speed. Let's make it 5. And that's something you just have to play around with because it depends on the scale of your scene and all that. And of course, let's not make a copy and paste mistake here. So let's change this to speed. And now we should see some movement. Oh yeah, and of course we have to play the scene. And there we go. Now you see the leftovers here. That's what I meant when I said on frame 0 it just keeps adding up. Those are the old particles that we created on the first one. There's actually a way to clean up your system. Well, there's 2 ways, but the simplest way is in the master system, and it's called free all particles. And that's just gonna wipe the entire thing clean. You've also got the free particle group, which is really useful and which cleans out the group for you. And it's one of the few things that's really much easier than in the C++ SDK, because there you have to, basically you have to write this yourself, and it's quite tricky, whereas here, super simple, you just pass in the group and it will just wipe that group clean. Because we don't have any group, we just use the free all particles. You see here that it says it should normally not be used, and you should set live and just have your particles die, which is of course correct. But on frame 0, this will have no negative side effect at all, and it's much more useful to us. So let's do this. So we get the particle system, and before we do anything else, we just clear out. Oops. Okay, now every time we execute this, we only get our 1000. It does not add up anymore, because before we add our particles, we throw away all existing ones, and there we get our movement. All right. So we've got speed now. We've got position in space. Let's also give our particles some mass and also a size. Okay, now so neither of these you will see within the particles. Let's add that first. Again, randomize it. So this size is just a kind of like a theoretical number. So our particle will not have or would not appear any different to the other particles, because like I told in the beginning, those are non-geometric objects. So these particles, they are more like a theoretical construct. But what you can do is you can feed your particles into a cloner object, and that cloner will then read that size and pass it on to the clones, which will then get different sizes. So you see here, when I execute that, all particles look the same. But now let's create a cloner, and let's see, let's put some spheres in there. Whoa, whoa, they are big. So let's make these spheres rather small. Okay. And switch the cloner into object mode, drag the clones, and there we go. And in that cloner you can change to standard TP. And now you see here, well, actually maybe 5 is still too big. Let's make it 3 for now, so we can see it better. Go back to 0 to create them. There we go. Okay, and there now you see the different size of your particles is being passed onto the spheres in the cloner, and your spheres then have different sizes. And of course your spheres are now attached to that clone. Yes, sorry, the spheres are now attached to the particles, and there you have a nice moving, interesting cloud there. Now, the mask doesn't really play into this right now, but we can do some more stuff with this. So we have created our particles, they have some velocity, but they're not yet being influenced by the outside world, and there's nothing really happening to them once we get started. So let's add some simulation. And we do that by using Espresso. Oh, that opened outside. Right, we only need a small window for that. So first step first is always to create a p-pass. And let's, to be sure, drag that group in. So that's passing our particles into that Espresso group. Let's create another group and make it a, oh, that's outside the frame. It's the p-wind. And we're feeding the particles in there. And wind expects an object as its base, so we just take that null object that we just created here, and there we have it. So we just leave it there. We put some turbulence in and some frequency for the turbulence. Makes the strength much less, so because when you have it at 100, the particles just blow away and they're gone. And now let's see what happens. Actually, let's make it spherical. It's much nicer. There we go. Now our particles are being more simulated. Actually, let's turn that to 0. Right, so there we have some turbulence in there. Nice. And this is now where our mass and size of our particles come into play. As you can see here, there's a mass and size dependency. And that means that by randomizing our particle size and mass, we also randomized, when we turn this to 100 here, we also randomized the influence that these kind of nodes, like the wind nodes, will have on our particles, depending on their size and mass. So, well, we really have randomized it as much as possible, and we play this now. This looks much different as before. And you can see that much fewer of these particles are now influenced by that wind node, by the turbulence. Okay, but there's still more to be done. We have our Espresso script here now, but we're not using any Python in here yet, though we can. By creating a node, and it's an Espresso script, Python, and this is just another Python script running within Espresso. And by default, it's with the standard inputs, you would normally just use it for some calculation and stuff, but you can just as well use it with thinking particles. For that, we remove the ports that we already have, because they just give us real or floating point numbers as input. But you can, actually let me put this in the middle so you can see it. You can use particle IDs for input and also for output. And let's call this PID, and this one here out PID. So when you hover over that port here, you can see at the bottom and the status bar that it's expecting TP particles, which we get from our P pass. So let's pass this in and take the output and pass it into the wind. So this is just feeding it in here and outputting the same ID back to wind. But we can do something with it in the middle. So let's look at that script that's currently in there. And, well, there's not a whole lot. Let me make this really small. So it's out of our way. Right, so currently this script is doing nothing at all. When we play it, well, apart from making everything a bit smaller, slower, it's not doing a whole lot. Let's see. Oh, we get error messages here. Oh yeah, that's because we renamed the ports, but by default automatically Cinema only changes the output port when you rename that. The input ports are not being renamed, so that's why it's still looking for input 2, which of course doesn't exist anymore because we threw it away. So actually we don't want to do this anyway, so we just pass in the incoming PID. And I think I already mentioned it before, the global keyword just tells Python that the variable out PID is a global variable and that we want to write into it. If we only wanted to read from it, that would be fine without the global, but because we want to write into it, and that's our output, we need to put the global in front. So that should always be the very first statement, so you don't forget it. And the input one, the PID one, that's available automatically. It's a global one as well, but it's coming in automatically, and since we're only reading from it, we don't need the global statement. And what we do now is just input equals output, so nothing. And since there should be no more error messages now, yeah, this is now much faster. So these errors, and actually the process of writing or printing these errors to the console, they are really sucking the speed out of your simulation, out of any script really. So that's something to keep in mind when you're using print statements for debugging. Always take those out or comment them out before you use your script in production, because these print statements really slow down your script a lot. Right, so just like before, when we created these particles, these PIDs are the same that we used to create them. So that means we can once again get our master system, of course only if we type it correctly, and then we can, let's say, oh yeah, you remember we played around in the cloner with the size of a particle. So let's look at that size. So let's call it current size equals, and that's again the TP master system, and this time we don't use the set command, we just use size. So it's not called get, but it's just called size, but this will return the size of particle with the PID, with the particle ID PID. And that's going to create or return a floating point value, which is the current size of that particle. And let's say if that size let's say if it's over 0.1, then make it smaller. For this we use the set size again. And take the current size and just decrease it by, well, just a bit. Actually, this should be the same. So what this does is here now, why did I choose 0.01 here and here? This means that if I decrease it by 0.01, at some point we will decrease it to the point where current size ends up being 0. So, well, actually, current size is 0.01, and we decrease it, so we end up with 0. So the next time we hit this loop at 0, we won't do anything with it. Or rather, what we are going to do is we want to get rid of this particle, because, as you remember, the life of our particle was set to 1000 frames. But once we hit the size of 0, we don't want to see it anymore, and we don't want to simulate anymore, because this will just eat up CPU power for nothing. So we just set the age of our particle to be a base time of -1, and that will kill it. Okay, so let's compile it. Oh yeah, I missed a colon there. Let's try this again. Okay, no errors. That is good. And, well, if we play it, because we can't see anything yet, but you can see some of them dying away. And at some point, they're almost all gone. Fantastic. So this set H definitely seems to be working. Let's turn on our cloner again. Then we have our differently sized spheres. And let's see what happens. And you should be able to see, look at this one here, for example, and now it's gone. There we go. So this is, well, it's almost like a dissolve effect. What can you use this for? I don't know. Anywhere really where you want your particles to slowly fade away, either by distance or by age. You can use this. Well, there are so many uses for this. One would be to, for example, emit them from this point, and then you could calculate the distance from this point to the particle, and the further it gets away, the smaller it gets, and then once it hits a certain limit, it's just gone. Plenty of opportunities there. There was another question in the forum, what to do with these Python nodes. Once you've written them, how can you access them? Unfortunately, as far as I'm aware, you can't add them to the new node here. But what you can do is, you can use X pools. So you can create a new pool, and, well, just call it whatever you like. I already created one called unnamed. You create a new pool, and then you can just drag and drop your node in there. And then the next time you want to create it, oops, not double click it, that's renaming, you just drag it and drop it back in. And as you can see, it's using the same ports, and let's make it smaller. And it also has the same script in there. So you can use that to to save your scripts. As I mentioned at the very beginning of this class, you could also implement this script as a Python tag, which then would mean it would work much more like a regular emitter. And that's what I did here. And I will give you both versions as part of this file and attach it to the class. But just to quickly demonstrate, so this will continuously generate these objects. And then what you get in the end, and I've rendered out something here, what you get in the end is, well, it looks almost like bubbles. Yeah, I'm sure you could use this for some very nice effect, like to, well, yeah, generate bubbles within water. It's nice and soothing. Okay, enough of this. So yeah, this is now using that tag, and the script is pretty much the same. I just adjusted a couple parameters like that the random particles are not being generated in a cube form anymore, but instead they're generated more like on on a plane, so it's more like a regular emitter. And yeah, they're more emitting towards this direction, not in all directions at once. But yeah, that's something to play around with in these settings here, and just play around with these parameters. You could create sliders, of course, for that. I didn't do this to save time. And I think we've seen enough now this week for you to get started yourself and use the Python generator and the other tags to create your own particles, and then work with Espresso, and again with Python and Espresso, and build your own script there. So I'm looking forward to what you guys come up with, and see you in the forums, and hopefully next week. Bye.